So what I'd like to do is share some ideas with you on what the challenges are in water, and then we'd like to look at what can we actually do about it. So I started off with saying, well, the problem is really too much water and too little water, and this is now happening almost in alternating years. So let's have a quick look on what I'm going to try to do. I'll give you a brief introduction, then I'll give you some examples of what is happening to climate, and then we'll look a little bit at land use, because I think what we have done wrong is we've either focused on climate or we focused on land use and never made the connection between the two, because I would argue from a hydrological point of view, land use changes might be more important than climate changes. And this is particularly the case in urban environments. So if you look at the green line, that's the population growth globally. The red line is the rural population, and the blue line is the urban population. And if you look carefully, we are now about here. So about 55% of all people live in cities, and this is going to go up to about 70% to 2050. That means 2.8 billion people will move into cities. Now think of that, and that's going to happen in the next 35 years. So urban demand for water is going to increase dramatically. But at the same time, demand for water is also increasing for all the other things we do, like mining, recreation, even forestry uses more water, and of course climate variability is the big unknown factor in this whole combination. So let me give you a little bit of an idea what is happening on the wet coast. I'm from the wet coast, right? We always think we have plenty of water, no problem. This is the reservoir for the Sunshine Coast, Chapman Creek. Supplies drinking water for 25,000 people. Close look at the reservoir. It's up in the mountains, about 1,000 feet above sea level. For those of you who don't know, here's Vancouver. Here's the Sunshine Coast. It's about a 35-minute ferry ride. Very popular area now because the properties in Vancouver are just out of the world. So everybody is moving to the Sunshine Coast. So in 2012, if you look at the reservoir, it was full in July, and look at the mountains, there was still snow on the mountains. And then in September, became a little precarious, and look what happened in October. In October, they were almost ready to fly up pumps, to pump the last bit of the reservoir over the weir so that people had enough water. 2012. So if you look at the blue line, this is the average precipitation over the last 50 years. And the red line is the precipitation in 2012. So if you look at it, you can see the winter time, pretty much the same precipitation. And then all of a sudden in July and August, we virtually had no precipitation at all. Moving forward to 2015, what I'm showing you here is the temperature versus the precipitation. And this is a 50-year record. And you can see 2015 was the hottest since our record started in the 50s. So what happened in 2015? Again, you can see pretty much the same precipitation, but then we had a very early spring. 1st of April, I was up in the watershed and there was no snow. And this is a snow-dominated watershed. And then you can see huge problems. Fortunately, because we did the study in 2012, they started to realize they're going to have a problem. And so they put in water restrictions the 1st of May. By the end of July, they had the level 4 of water restrictions, which meant no water can be used for outdoor purposes. Now imagine if somebody comes to you and says, you can no longer use your water for your garden and for your trees and for whatever you do. And fortunately, they got sufficient rainfall to bail them out. Now, if you look at what does that mean for the future. So the first 2012, you can see we had a late summer drought, and in 2015 we had an early summer drought. And each one was different, and each one had to be handled in a different way. So if you look at what is happening to the average temperatures, you can see in all cases the temperatures are actually going up. And if you look at the precipitation, on the left side is the summer, on the right side is the winter precipitation, and on the bottom is the snowfall. So they're all telling us it's going to get warmer, we're going to get less snow, and less precipitation. And this is an area which is growing massively, right? Now, what is particularly critical is the fact that this is a snow-dominated watershed. So if we get no more snow, and we still get a lot of precipitation, that means the peak of the runoff is going to go earlier in the year, and then you're going to have less water in late summer. And we already see that shift. The Fraser River now peaks 2 weeks earlier than ever before. And so gives you a bit of an idea some of the challenges these people are going to face. The other thing you need to know is what temperature is actually increasing the most. So we can look at the extreme minimum, the mean minimum, the mean maximum, and the extreme maximum. And so the red one is the mean maximum, and the blue is the mean minimum. And if you plot it up in this way, the blue is the mean minimum. And remember, the climate people told you that the temperatures are going to increase on average about 2 to 3 degrees. The minimum temperatures in these mountain watersheds are increasing by 4 to 10 degrees. And that means less snow and obviously a very different hydrological regime. So what options do you have? Well, you can enhance the storage. You can go to massive conservation. You can look for new water sources, or you can recycle and reuse. Now, each of these options is challenging. Looking for in improving your storage is very expensive. You know, look at the kind of money it takes to build a Site C in the Peace River. We're looking at $7-8 billion, right? Conservation is the easiest thing to do in the short term, but it means we have to persuade everybody to change their behavior. Looking for new water sources becomes really challenging. If you're in the Okanagan, there is no new water source because every water source is already being used. And then recycling and reuse is okay, but again, if you have to replumb your whole system, that's also a big challenge. So you can see we have options, and my argument is we need to look at all of these, not just one. So that gets me to the hydrological cycle. You all know about the hydrological cycle, and I divide it into the blue cycle and the green cycle. Everybody knows the difference between blue water and green water? No? Okay. Blue water is the rainfall which hits the surface and goes into rivers, lakes, and seeps into groundwater. That's the water which you use. That's the water which we manage. And then there's the green water. That's the rainfall which hits the vegetation, goes into the soil, and evapotranspires up into the atmosphere. So how much water do you think goes into the green cycle, and how much goes into the blue cycle? Any guesses? Remember, we use blue water, right?
70-30.
Right, about 30%. So if you look at the rainfall, hits the surface, about 2/3 go into the blue cycle, and then it gets evapotranspired back up. And only 1/3 goes into the lakes, rivers, and groundwater, which we use and which we manage. We don't really manage the green water very well. And this is probably the foundation for innovative stormwater management. It's the foundation for everything we do with innovative water management. Green water management, and I give you a couple of examples why this is so important. We had a project in Egypt, in the Sahara Desert. They had to settle 100,000 Bedouins, and the Bedouins wouldn't give up their animals. And this is an area where you get 200 millimeters of rainfall, very dry, about 5 storms a year. So the first project was to do underground cisterns and collect the first few storms we get and collect the water in the underground cistern so that people and animals have water. But then the animals need feed. And so how do you actually do this in an area where you have no rainfall and overgrazing is a problem? So if you put these stupid little barrages in there, you can actually store the water for 2 or 3 days, and that is enough water to go into the soil that you can grow a crop of barley. Simple as that. If you don't do it, the water goes through it very fast and is gone within 24 hours. That's green water management, and that's what we need to start looking at. The next thing about green water management is soils, and nobody wants to deal with soils because you were told from the moment you were born that it's dirty and you don't want to deal with it. Right? Well, look at the red line and the blue line. And the bottom tells you sand, loam, silt, clay. So the area between the red and the blue is how much water the soil can hold when it rains. And that's the water which vegetation can use. If you then add organic matter, which is the black line, you can see how much more water you can actually store in the soil for future use. And this is absolutely critical because what do wetlands do? Wetlands are organic matter. And a gram of wetland can hold almost 1,000 times its weight in water. It's like a sponge. If you put your sponge under the sink, the first minute, water doesn't flow through the sponge, it holds it. And that's really the critical part for water management in a watershed context. So if you look at soil carbon, it is not only that it can hold a lot of water, but soil carbon also creates a soil structure that allows the water to infiltrate. It also has storage capacity, has a lot of negative charges. It can hold nutrients. And remember, everybody is talking about too much CO2 in the atmosphere. If you can store that CO2 in organic humus, you're actually helping the CO2 emission. So if you drain a wetland, you're generating huge amounts of CO2. If you help increase the organic matter in the soil, you can actually help the whole process. So I am quite adamant that we should start thinking about soil and wetlands because these are the 2 key components we do. And remember, wetlands have a very bad reputation. If you read the British literature, you will find out that people disappeared. There are ghosts in there. It smells like hell. Have you ever dug a soil pit in a peat? You can smell the hydrogen sulfide, right? So we've given it a terrible reputation, yet it is the best water storage system. It is the best carbon storage system, and it helps you manage the water. And in urban stormwater, you will see later on, it actually helps you tremendously in water pollution. Just to give you an idea how important the soil is, we have lots of lawns. Somehow or another in Vancouver, people are completely preoccupied in having a green British lawn. Do you realize that we use 45% of domestic water on an annual basis for watering lawns? Bacteria-free water? Total insanity, but everybody insists on it. So what is the first thing you do when you have a new development? You remove the topsoil. Then you bring in the bulldozers and you compact everything. And then you build the house, and what's the very last thing you do before the real estate guy comes and sells your house? you roll out the turf.
Half of it.
That much soil, right? So Richard Bowes in North Vancouver did this interesting experiment. He put 30 centimeters of topsoil and the turf, 3 centimeters or so, and he didn't water it for 3 months. So look at the difference. By simply storing that water in the soil, you don't need to irrigate. In fact, my wife told me I should talk about this in a totally different way. We shouldn't really water lawns in July and August. It will turn yellow, and the first rain, second rain, within a week or two, it's green again. And she told me, women like gold, right? So why don't we like golden lawns? It's a very stupid idea, anyway. The only reason, and it's again a stupid idea, the only reason why people are so preoccupied with green, have you ever looked at your eyes? Your eyes can see from blue all the way to red. But you can distinguish more green shades than any of the other colors. And that might be one of the explanations why we are so preoccupied with green stuff. Okay, so now we go to climate, because the climate is really very, very important right now, because we have done a bit of a bad job. You probably still have deniers amongst you, but I hope you're all enlightened. So what is happening now is 2016 was the warmest globally, 2015 was the second, and 2014 was the third warmest. But we did a terrible mistake. We told everybody that the average temperature is going to increase by 2 to 3 degrees. I think that's absolute nonsense, because if you walk from here over there, and there's a 2-degree difference, you won't even notice it. What we should have done is told people, when do you worry about water? When it's too hot, or too cold, or too wet, or too dry. The variability, the extremes, is really what you have to worry about. So we could look at this in a different way. We could look at this in terms of low to high temperatures. This is like we grade students, right? We have some dumb ones down here, and we have some really bright ones over here. And then this is the average, right? So we always, in a class, we say the average is such and such, and the low and the high, right? So if you look at this at temperature, we said, well, it's getting warmer, so that curve is shifting in this direction. That means we're now getting no more cold temperatures, and we get lots of hot temperatures, right? What is now happening is I'm getting a lot of dumb students in my class and a lot of bright students, which means that curve is now going flatter. There are less students on average, but we have more in the low end and more in the high end. So this is how the curve is changing, right? If you then shift that from this to this, you can see that we still are getting cold temperatures, but we get more hot temperatures. And so the people who are now saying, well, the winter in the east has been terrible and global warming is no longer the case, we still are getting that, mainly because we get more extremes. Is this actually happening? Can I prove this to you? Here's some data from the United States, starting from 1900. Each one is a decade. The red is the extreme maximum temperatures, and the blue is the extreme minimum temperatures. And for those of you who are old enough like me, the 30s was extremely dry. So you can see we had lots of hot temperatures, but relatively few blue temperatures or cold temperatures. Now look at what has happened over the last 4 decades, from the 70s, 80s, 90s, 2000s. Lots more hot, but still quite a few extreme cold temperatures. So what is happening is the extremes are increasing, and that is the problem for water management. Here's data from the insurance companies for the United States. Major floods. 2016, they had 19 major floods. And you can see the history since the 70s, I think, 80s. clearly an increase in the number of floods. What is even more interesting is this: 24-hour precipitation changes. That means how much rain are you getting over a one-day period? And if you look at the trend, it's clearly up. So we get more intense rain over a short period of time. Remember the Calgary flood, but what people didn't even look at is the Boulder flood in Colorado. That happens in September of the same year. Boulder, Colorado is located just about at my alma mater, just about the same condition as Calgary. Mountains in the back, and right at the foothill is the city. 100-year record for the precipitation in September. Look at what happened in 2013. This is an incredibly unusual event. Just to give you an idea what this event was like, in one day they got 230 millimeters of rainfall. I don't know what the average rainfall is here, but it's probably about 300. I don't know. But anyway, they got 230 millimeters in one day. And if you take the first day, the second, and the third, so this is the first day, the second day, the third day, they got 340 millimeters in 3 days. And on average, they get about 43 millimeters over a 100-year period on average. And on the annual precipitation in Boulder is 480 millimeters. So in 3 days, they got about 2/3 of the rainfall which they normally get over a year. And you can imagine the kind of challenges that provides. Moving closer to you, this is Caslow, up in the Rocky Mountains near Nelson. 100-year record. The highest precipitation happened in 1963. And this is what we use as a basis for stormwater management, 100-year flood. In 2015, 2005, 2012, and 2013, we had between 30 and 70% more rain over the same time period. Totally different situation. So all of you know California's drought. So I want to show you the extremes which are happening right now. What I'm showing you here is the annual precipitation cumulatively on average over 100 years. So this is the 100-year average precipitation in Northern California between 8 stations. The 1930s, when we had the drought, was the lowest. And 2013 and 14, the peak of the drought in California was about here. So about at least 30 to 40% less rainfall than the average. Moving a few years ahead, 2016, 17, right now, this is the February data. Right now, the Northern California situation is here. This is the absolute maximum they ever observed. And you have heard about all the flooding which is going on. So we went from an extreme drought to an extreme flood all within a 2 or 3 year time period. And this makes it even more challenging because when you have a long drought, the soil becomes desiccated and they become hydrophobic. They repel the water. And so you then get a big, massive rainfall. That stuff is going to run off much, much faster than if it didn't happen. If you have a lot of organic matter in there, it might help you. Now let's go to drought. And let's see what has happened to drought, which is fascinating to me. 2016, some of these places have reached temperatures of 50, 54 degrees. How many of you have ever been in a sauna? Nobody goes into saunas anymore, right? How hot do you think the sauna is? About 50, 60 degrees. How long do you stay in there? About 20 minutes at most. How would you survive if you don't have air conditioning when you have a few days of 50-degree temperatures? I don't think we would survive. Remember, your blood temperature is about 38, right? So let's have a quick look at what's happening around the world in terms of drought. So again, here is your stupid people and bright people converted into temperatures. This is in Europe, and remember 2003 was this really hot year in Europe where a lot of old people died because they couldn't handle the heat. So that was here, but look at what has happened in 2010. It was even more extreme. You think that's only once in a place? This is 2011, I think, 2010 in Moscow. Totally extreme situation in terms of drought. This is Texas in 2012, 11. Again, this is precipitation versus temperature, a 100-year record. This was the hottest and the driest ever. So you think Vancouver has a lot of water and we don't have to worry about it. This is 2015. Again, this is the summer temperatures versus the precipitation. 50, 60-year record. Here is what happens last summer, 2 summers ago. So that gets me now to the Columbia Basin, and I will tell you a little more about the Columbia Basin because I'm dealing there with lots of small communities and they're all concerned about water management in spite of the fact that everybody thinks there's plenty of water in the Columbia Basin because they're all in the mountains. Again, we did a study on 14 municipalities over a 7-year period from 2009 to 2015. And over these 7-year periods, they had one of the hottest and 2 of the wettest periods ever in 100 years. Many of these communities have a 100-year record because they were mining communities where they started measuring. So this is Caslow and this is Nelson. And in both cases, the extreme events meant massive flooding in their downtown area. In fact, for one of the floods up in Caslow, it wiped out the complete intake of their drinking water. So what is really critical is the fact that the high mountains are actually warming up faster than the lowland. And if you look at this in terms of elevation, this is elevation, and this is January, February, March, April, May, June, and so on. And you can see it's the late winter which is warming up faster. And again, that is the problem for snow. It's going to convert into rain. So are these extremes happening at the same time? Here's the one example I can show you, which is probably the most illustrative one. The US has something like 7,000 hydrometric stations measuring the flow of rivers. And they're all online and you can look up the real-time data any day. In 2011, all the black and the blue dots were river stations which were in a massive flood conditions. And all the red and the orange ones were stations were in a complete drought. So this is at the same time in a major river basin, you had massive floods in top and totally dry conditions in the south at the same time. I've never experienced that before because usually it's one or the other. So remember, floods and droughts are really the challenges for us. And floods we can actually predict a little bit and we can give people a bit of notice when these things are happening. But this is very different with droughts because in droughts you never know when they start and you never know how long they will last. If you look at California, they had no idea when it's going to stop. And so these two things really create the biggest challenge for us down the road. So here are all the water challenges for the climate variability, and we can do all kinds of adaptive measures, which I'll talk a little bit more about. So have I depressed you now? Are you completely depressed? Well, let's look at some ideas now what we can actually do about this. So let's look at land use. So the main thing is this chart here. This is the impact of land use on water quality, and it is the impact of land use in terms of water use. So forestry obviously doesn't use a lot of water, and if they do it right, they don't pollute very much. But look at these two. Agriculture is now the biggest water user, and is also the biggest water polluter, followed by urbanization. So we should really focus on these two things, and I suspect in the Red Deer River watershed that is going to be the big issue, urbanization and agriculture. This is the most important graph. If you don't remember anything, remember this. What I'm showing you here is what is happening to the rainfall. When the rain hits the surface, it can either evaporate or evapotranspire in green, or it can run off the surface in red, or it can go into the soil, or it can go into groundwater. So if you're in a forest, you can see the distribution, a lot of evapotranspiration, but also a lot of storage in the soil, and water is retained because usually you have good organic layers and so on. If you now move from a forested system all the way to an urban system where everything is impervious, look at what happened to the red, which is the surface runoff. And what do we do in the urban system? We pipe everything into the stream, right? Get rid of it. You don't want to go into a parking lot when there's that much water. You want to get rid of it, right? We told the engineers to do that, and they were very efficient in doing it. And now we need to rethink this idea. So remember, land use change, particularly in the urban environment, drastically changed the hydrology. How fast is this change happening? This is over an 11-year period. You see on the left-hand side, most of it is forested. On the right-hand side, it's all urbanized. So think how we have changed the impervious surfaces. That means all that water is no longer infiltrating, it's going to run off. So typically what we say in a forested system, when it rains, the river responds like this. It comes up slowly and then goes down. Well, if you make it impervious, you get more surface runoff. It's going to come much faster after the rain starts. It is much higher, and then we have much less afterwards. So that means we're creating more extremes in our river system. We're completely preoccupied with bigger houses. Everybody wants a bigger house these days. So look at this. Here's an old house, old and decrepit like me, and then it's converted into 2 subdivisions. How much do you think the impervious surface has changed by doing that?